All right, welcome to day two of the second semester review. Today we'll be covering problems 17 through 32 in your packet, the double-starred questions. So we'll start here with problem 17, converting from intercept form to standard form. So for this one, the first thing we need to do is multiply the binomial. And problem 16, we did a similar process and we used the box method. So for this one, I am going to use the FOIL method. So we're going to take x times x squared, x times -4 gives us minus 4x, 7 times x is plus 7x, and 7 times -4 is -28. Now for me, the next thing I would do is combine my like terms. So I still have that -2 out front. I get plus 3x minus 28. And now the last step, distribute the -2. And now our equation is in standard form. Let's see, the path of a ball is launched in the air is modeled by h of t is equal to -16t squared plus 24t plus 5, where h is the height in feet and t is the time in seconds. How long does it take the ball to reach its maximum height? This is really asking, find the axis of symmetry. So from our equation, normally for axis of symmetry, it's x equals. We're going to use t equals because t is our variable. 2 times b. Nope. Let's try this again. The opposite of b over 2 times a. So the opposite of 24 divided by 2 times -16. So -24 over -32. And if I divide this, -24 divided by -32, it's 0.75, and time is in seconds. What is the maximum height? So now this is the y coordinate of the vertex. So all I'm going to do is I'm going to take my height equation and I'm going to plug in 0.75 for t. So -16 times 0.75 squared plus 24 times 0.75 plus 5. So what I'm going to do is I'm going to plug that into my calculator because much easier for the calculator to make that calculation. So I am going to change the sharing. And our equation, -16 times 0.75 squared plus 24 times 0.75 plus 5. And we find our answer to be 14. So that would be 14 feet is the maximum height. The last part of Unit 8 was our comparison of linear, exponential, and quadratic functions. And you can see the definitions and some things, some examples. So a linear function is a straight line, which would be y equals mx plus b, or ax plus by equals c. And if we have a table, the first difference is a constant. Exponential curves up or down. The equation y equals a times b to the x. And the table has a multiplication pattern. You're always multiplying by the same thing to go from one y value to the next. And the quadratic, y equals ax squared plus bx plus c, or y equals a times x minus h squared plus k, or y equals a times x minus p times x minus q. The table of values, if you take the second difference, that would be a constant. And we'll look at those as we go through some examples. So if we look at the graph for A, hopefully you can see this is a parabola. It's a U-shaped curve, which means this is quadratic. The table. So let's check first. We'll look at the first difference. So we take 2 minus negative 3, which is 5. 7 minus 2 is 5. 12 minus 7 is 5. That's what we call the first difference. The first difference is the same, and according to our table above, that means it's linear. Try this again. Linear. There we go. Here are some graphs. A value to the power of x. X is in the exponent. That makes it exponential. 3x minus 5y equals 15. This is our ax plus by equals c. That would be linear. And 3x squared minus 1. So as soon as you see the x squared, that's quadratic. All right, on to Unit 9. Solving quadratic equations by factoring. Yes! In order to do that, the first thing we need to do is write the equation in standard form. It must be equal to 0 before you factor it. That's because of step 3, that zero product property. Factor the quadratic equation. When you're factoring, the first step, always check for a greatest common factor. If a is equal to 1, factor using the x method. If a is not equal to 1, use the slide method. If it's a difference of two squares, a squared minus b squared, factors to a plus b, a minus b. And then once you have it factored, you can use the zero product property to solve it. Set each of your factors equal to 0 and solve for x. So here we go, 23a. I do not have a greatest common factor other than 1. And a is equal to 1, so I can use the x method. I need to find two numbers that multiply to 28 and add to negative 11. In this case, because they multiply to something positive, my numbers have to have the same sign, and they add to something negative, so both numbers have to be negative. And two numbers that multiply to 28 and add to negative 11, negative 4, and negative 7. And again, if you don't know that, go ahead and write your factor pairs for 28. So my factored form, x minus 4 times x minus 7 equals 0. Now I use the zero product property, x minus 4 equals 0, x minus 7 equals 0. And one of the things I really love about the x method, my solutions are just the opposite of the sign of my factors. So x minus 4, the solution is x equals 4. X minus 7, the solution is x equals 7. And we are done with that problem. If I look at letter B, here we're looking for two numbers. Again, greatest common factor, there isn't one other than 1, and A is 1. So now I want to find two numbers that multiply to negative 45 and add to negative 4. In order to multiply to a negative value, we have to have one positive number, one negative number, and they have to add to something negative, so the negative factor has to be the larger factor. Again, you could list your factor pairs, 1 and 45, 1 and negative 45. 2 doesn't work. 3 and negative 15. 4 doesn't work. 5 and negative 9, and those add to negative 4. So we have x plus 5 times x minus 9 equals 0. Set each factor equal to 0. And again, we get the opposite. So this is x plus 5. So x is equal to negative 5. X minus 9, x equals positive 9. And those are the two factors. Two x squared minus x minus 6 equals 0. Again, if I look for a greatest common factor, I don't have a greatest common factor other than 1. Tempted here to look at 2, but this middle term that has a coefficient of negative 1 is not evenly divisible by 2. So that means now A is not 1, so I'm going to use the slide method. Take the 2, slide it to the end, and multiply. X squared minus x. 6 times 2 is 12. Find two numbers that multiply to negative 12 and add to negative 1. Let's see, 1 and negative 12. 2 and negative 6. 3 and negative 4. There's my pair. Negative 4 and 3. In order to get that pair of factors, I multiplied by 2, so now I'm going to divide by 2. Is negative 4 evenly divisible by 2? Yes, it is. Negative 4 divided by 2 is negative 2. So one of my factors is x minus 2. Is 3 evenly divisible by 2? No. Is there a number that evenly divides into 3 and 2 other than 1? No. So the 2 in the denominator goes in front of the x, and the 3 becomes the constant factor that we add to the 2x. Zero product property. X minus 2 equals 0. 2x plus 3 equals 0. I'll actually show it with this one, but it's just like the x method. We get the opposite value, x equals 2. 2x plus 3 equals 0. I subtract 3 from both sides. 2x equals negative 3. Divide both sides by 2. X equals negative 3 over 2. And there are my two solutions. The next unit, the next lesson was on simplifying radicals. So you can simplify radical expressions using either the factor tree method or the perfect square method. For the factor tree method, make a factor tree for the numbers under the radical, circle pairs, and box the leftovers. The pairs go outside the radical, one number per pair, and the boxes stay under the radical, multiply the numbers together. The other thing with the factor tree method, the numbers you're going to use for your factor tree, 2, 3, 5, 7, 11, 13, 17. I think that should cover it all. But those are all prime numbers. They only are divisible by 1 and themselves. This 11 looks really bad. I'm going to rewrite that. There we go. For the perfect square method, find the largest perfect square that divides evenly into the number under the radical. Rewrite the radical as a product of this perfect square. Simplify by taking out the perfect square. And we'll take a look at one example of each. So the square root of 32, if I use the factor tree method, I start with 32 and I check, is it divisible by 2? It is because it's even. 2 and 16. And now I forget about the 2 for a while and I focus on the 16. Is 16 evenly divisible by 2? Yes, because it's even. 16 divided by 2 is 8. Is 8 evenly divisible by 2? Yes. 4 times. Is 4 evenly divisible by 2? Yes, twice. So now I circle my pairs and I box my leftovers. So the square root of 32 has a 2 from this first pair of factors and another 2 from the second pair of 2's. And under the radical is that leftover 2. So we go ahead and multiply 2 times 2 to get 4, square root 2. And that's our answer. 2 times the square root of 63. If I use the perfect square method, I'm going to find a perfect square and whatever other number it multiplies by to get me 63. Now, I should actually check first, is 63 in my list of perfect squares up here? Unfortunately, it's not. So then I'm going to start with 49 and check, does 49 divide evenly into 63? And I start with 49 because that's the perfect square. It's the largest perfect square that's less than 63. Unfortunately, it does not divide evenly into 63. So then I check the next one down, 36. 36 does not evenly divide into 63. Then I try 25. 63 divided by 25 does not come out even. 63 divided by 16 does not come out even. 63 divided by 9 does come out even. And 63 divided by 9 is 7. So now I take the square root of 9. Now I have that 2 that's out front already. Square root of 9 is 3. The 7 stays underneath the square root. 2 times 3 is 6. Square root 7 is my final answer. So why is this helpful, or when is this helpful? It's helpful when you get an equation that has x squared and no x to the first power. So if I have x squared minus 16, to solve this, I can use the square root method. I can add 16 to both sides. That way I get my x squared by itself, which says right here, get the x squared by itself. Take the square root of each side to undo the squared. Put a plus or minus in front of the answer, then simplify the square root. The square root of x squared is x. 16 is a perfect square. The square root of 16 is 4, so I get plus or minus 4. So I have two solutions, positive 4 and negative 4. Example B. I add the 27 to both sides of the equation. I don't have the x squared by itself yet, so I'm going to have to divide by 3. Now I have the x squared by itself, and I can take the square root, and I'm going to put a plus and minus in front of the square root of 9. On the left-hand side, the square root of x squared is x, plus or minus square root of 9, 3. There are my two answers. Then from there, we went to completing the square. To turn an expression x squared plus bx plus c into a perfect square, c has to be b divided by 2 squared. Once you complete the square, you can write it as the square of a binomial, x plus b divided by 2. So let's take a look. Find the value for c that makes the expression a perfect square, then write the factored form. So my value for c has to be negative 16 divided by 2 squared. Negative 16 divided by 2 is negative 8. When I square negative 8, I get positive 64. C will always be a positive number. The factored form, now I could either take x squared minus 16x plus 64 and use the x method to factor, or I can use this little shortcut up in the directions that says I take x plus b divided by 2. Well, b divided by 2 is negative 8. So it's not going to be plus, it's going to be minus 8. That whole thing squared. And that's completing the square. Then we talked about the discriminant and the number of real solutions a root has. So the discriminant is actually part of the quadratic formula, and it's the part that goes underneath the square root symbol. It is b squared minus 4ac. If b squared minus 4ac is positive, we have two real solutions, or real zeros. And that means our graph crosses the x-axis twice. It could be upside down as well, but I'm just going to draw it right side up. If the discriminant is 0, we have one solution. This would be a graph that comes up and touches the x-axis but does not cross. But it does touch at that one point. The vertex is on the x-axis. And if our discriminant is negative, we have 0 solutions. This is a graph that does not ever touch the x-axis. Might look something like that. So calculate the discriminant, state the number of solutions of each equation. So for the discriminant, I am going to list my values for a, b, and c. 2, negative 3, 5. My discriminant is negative 3 in parentheses squared minus 4 times 2 times 5. It's the exact formula that we have at the top of the page. If you would like, you can actually have your calculator multiply that out for you. I'm going to actually do it by hand here. Negative 3 squared is 9. 4 times 2 times 5, well, it's easier for me to do 2 times 5 because that's 10 times 4 is 40. 9 minus 40 is negative 31. So my discriminant is negative 31. That means I have 0 real solutions. My second example, a equals 4, b equals 20, c equals 25. So my discriminant, 20 squared minus 4 times 4 times 25. 20 squared is 400. And again, here, if I take the second 4 times 25, that's 100, times 4 is 400. 400 minus 400 is 0. So I have one real solution. We can also determine the value of the discriminant, whether it's positive, negative, or 0, just by looking at a graph. Here, our graph just touches the x-axis. That means we have one solution. And back on our table, it said if we have one solution, our discriminant is 0. Which I said the discriminant is just the part that leads us into the quadratic formula. So to use the quadratic formula, we write the equation in standard form equal to 0. Label A, B, and C. Calculate the discriminant, D equals B squared minus 4AC. Then substitute the numbers into the quadratic formula. And again, this is one version of the quadratic formula, the opposite of B, plus or minus the square root of D over 2A. For approximate solutions, use a calculator to evaluate the expressions, one for the positive, one for the negative, round to the nearest hundredth, 2 decimal places. I prefer to do the opposite of B over 2A plus or minus the square root of D over 2A. Just a personal preference if I'm not rounding my answers. So for number 30, we need to get this equal to 0. So I can do that by subtracting 9x. 7x squared minus 9x minus 20 equals 0. A is 7, B is negative 9, C is negative 20. So my discriminant, negative 9 squared minus 4 times A times C. Negative 9 squared is 81. 4 times 7 is 28, times negative 20 makes this plus 560. So we get 641 for D. So I know I'm going to have 2 solutions. My solutions are going to be the opposite of B, the opposite of negative 9, which is 9, over 2 times A, 2 times 7, plus or minus the square root of 641 divided by 2 times 7. Two times 7 is 14. So if I take a look, been a while since I used the calculator, so it of course shut down. So 9 divided by 14 plus the square root of 641, arrow out of there, divided by 14. Make sure you arrow out or the division is going to be underneath the radical. That's not what we want. And it says 2.451. That 1 tells me take that 5 and leave it alone. So 2.45 is one of my solutions. My other solution, I like that second enter to bring that equation back. I'm going to use second and the left arrow to go all the way over to the left. And I'm going to arrow back over. On top of that addition sign, I'm just going to make that a subtraction. then second and the right arrow to get all the way over to the right and hit enter. And I get negative 1.165. That 5 says, hey, look at that 6 and add 1 to it. So negative 1.17. Those are my estimated solutions, and the fractions are my exact solutions. Unit 10, we started with rules for exponents, and they are all listed there. I am going to leave that. I'm not going to read through each of them. But this double star here, you are done simplifying when each variable appears just one time and all exponents are positive. Undo negative and zero exponents using the last two rules. So use properties of exponents to simplify each expression. Each variable should occur once and all exponents should be positive. So here we have a to the fifth, b to the second, that whole thing raised to the third power. So that is the third rule and the second rule both. So we're going to have a to the fifth raised to the third and b squared raised to the third. Power to a power, that's the second rule. And we multiply those exponents. So a to the 15th, b to the 6th. 3x to the 0. Now this is one that a lot of students struggle with. You have to almost think of this x as being in parentheses. So we have the 3 out front. X to the 0, according to our second to last rule there, is 1. So 3 times 1 is 3. Eight m squared n times 3m to the third n to the fifth. Multiply the numbers in front. 8 times 3 is 24. M squared times m to the third, that's this first rule. It says we add 2 plus 3 is 5. N times n to the fifth, well, that n is really n to the first power times n to the fifth power. So we add 1 and 5, we get n to the sixth. With negative exponents, I always just start moving things around. The negative 2 does not have a negative exponent. It's going to stay in the numerator. X to the negative fifth, that exponent is negative. It's going to move from the numerator to the denominator. Y to the third does not have a negative exponent, so it stays in the numerator. Z to the negative fourth moves to the denominator, and the exponent becomes positive. Six c to the fifth times d to the fourth, all divided by 3c squared d. So the first thing I would do, divide the numbers if I can, or reduce the fraction. 6 divided by 3 is 2. The rule when we divide is this fourth rule here. We subtract the exponents. So we take 5 minus 2. That gives me c to the third. Remember, the d in this denominator is a 1. So we have 4 minus 1, which is also the third. And that is my answer for that one. Rational exponents are just a way that you can write an exponent as a fraction, and it actually is the same as a radical expression, where the denominator of our exponent becomes our index, and the numerator stays as our power. And there are two different ways that you can write those, with parentheses or without. So we are going to rewrite with rational exponents. And the last step is always going to be, can I reduce that power? So let's see, x, 4 is the power, it goes in the numerator. 3 is the index, it goes in the denominator. Can I reduce 4/3? No. There's my answer. The square root of y to the 9th. Remember, square root, even though it's not written there, it's like there's a 2. So the 9 is the exponent, it goes in the numerator. The 2 goes in the denominator. Is there a number other than 1 that evenly divides into 9 and 2? No. So that is as simplified as that one gets. And that is the end of the day 2 review. Now you can go back and work on the non-double starred problems, and that's your homework.